So we just finished looking at inductors, and remember the job of the inductor is to store energy in its magnetic field. Here in this video we're going to have a little bit closer look of magnetic energy. Now, from circuit analysis, we understand that the energy stored in an inductor is Li squared. Right? And that's true. That certainly holds. If you have the inductance L and you know the current through it I, then you're good to go. That's the energy in that inductor. However, in our course, electromagnetics, we want to be able to relate this energy to the flux density and the magnetic field intensity. So how is the energy related to those two things? How is magnetic energy related to the magnetic field, right? I mean, that seems like a rudimentary question. How is magnetic energy related to the magnetic field? And that question is what we're going to answer here. Now, let's consider a small differential volume. So I'll draw it out here. Just my drawing skills are terrible, but let's say that on the top we've got current maybe coming out at us. That current, we'll call that current I. And then also we're going to be talking about a loop, although we're not going to explicitly show the loop in our little differential element. But the idea with the loop is that the current then would be going into the page on the bottom of this differential surface element. And I could show my axes here, x, y, and z, but they're as you would expect. And so I'll just show that this dimension is delta x, and this dimension here is delta z, right? And then this dimension here is delta y. So this guy in our material is delta x, delta y, delta z. That is its differential volume. So we're saying it's covered in conducting sheets on the top and the bottom. And it's got this current, we could call it delta I. Let's call it delta I. Makes more sense that way because it's just a little differential piece of a larger volume. Now, if each differential volume, or if this differential volume has this current, then it also has a flux through it, and it has then an inductance, and we'll call it a differential inductance, delta L. So that would be, based on our definition of self-inductance, that would be delta psi over delta I, right? The flux divided by the current. And I'm not using a capital N here because we don't have loops. So we're just talking about one little piece, right? But it's flux, and if you have multiple loops, then it's N times that flux because it's the total flux. Okay, so here we just have this one loop where current is coming out at us and then going into the page. So as this magnetic field circulates around this I, according to the right-hand rule, the flux enters which surface area are we talking about? So I want you to kind of think about this. So use the right-hand rule, and we have 6 faces on our cube, and think about which face is the magnetic flux entering. So you can think about this current on top. Use the right-hand rule, answer that question. Which face is the flux entering? Okay, so hopefully you thought about it. If not, pause the video, think about it some more. But the flux, according to the right-hand rule, if you point your thumb of your right hand out of the screen, then your fingers are circulating in the direction of the magnetic field. So this guy has a magnetic field that's circulating around, and so it's actually coming in to this face here, which is given by delta x, delta z. right? And same thing with this bottom one too, by the way. So the current is going into the page, so it's circulating like this, and it also enters delta x delta z. So we can write the flux, and we're going to assume that this thing is so small. This is why you take a differential volume. It's so small that the flux is the magnetic field is approximately constant, and it's normal, or it goes through this surface at a normal angle of incidence, and it doesn't change direction anywhere in there because again this thing is so small, right? And so what we could do is we could write the flux as mu times h, which is b, right? And then b times the area. And we argued already. I had you pause the video, and you told me that hopefully you told me that the face was delta x delta z, and so that's the area of that face divided by delta I. Now, about that delta I, one can use Ampere's law. We've done it actually before, but we're not going to do it here, to show that current delta I is actually the field H times delta Y, right? So it's the field is going this way in our differential element, and how much is it going that way? Remember, Ampere's law is that line integral h dot dl, and it's going delta y that way. So now the h's cancel, which is nice, and we've got mu delta x delta z over delta y, and that's the inductance of this little element here. All right, now remember we're interested in the energy, so let's bring that W back. So the energy in this little guy, and that's a delta, in this little guy is 1/2 times the delta L times delta I squared, right? We said the energy is, again, here is 1/2 Li squared. So we're just talking about deltas here, differentials. So this is 1/2 mu delta x delta z over delta y, then h squared delta y squared. Remember, for the same reason, remember delta I is h times delta y. So that's h squared delta y squared, and then when we cancel one of the delta y's, we get 1/2 mu h squared delta x delta y delta z. That looks familiar, right? What is that? That's 1/2 mu h delta v. That's the volume of this thing. Nice. All right, so that's the energy contained in this differential element. So what we're going to do is define what we're going to call the magnetostatic density, just like we defined the electrostatic density at some point. And I even drew the E. I meant to draw an M there. So this is a lowercase w and a capital M subscript. This is the magnetostatic energy density. So it's how packed is your energy in your object, right? And so we've already been working with differentials here, so the differential tells us how packed or how dense the energy is, and we're going to define it as the limit. We're going to take this differential element to 0, and we're going to take that delta W over delta V. So you see it's energy per volume, and then we shrink the volume. So it's like the energy at a point. That's why it's a density. And so when we do that, right, we've got the limit as delta V goes to 0, and our energy is 1/2 mu h delta V over delta V. So that's good. We don't have an issue with taking delta V goes to 0. We get 1/2 mu h, that should be mu h squared. This should be h squared, by the way. Okay, so that is the energy density. That's good. Now, let's just consider a little bit more. Let's go a little further. Let's bring the flux density into this. So this is the energy density, little w, we can write this as mu h, of course, then times h again, because it's h squared, and I can write mu h, that's B, the flux density, right? And because B and H, I'm going to try to bring in the vectors here, because B and H are parallel, right? This is the magnitude of B times the magnitude of H. Well, that's just B dot H. Remember, the dot product is the magnitude of one times the magnitude of the other times the cosine of the angle in between. But B and H are parallel with one another, so the cosine of 0 is, of course, 1. So now you see we've brought in B and H. Remember, our original question was how are B and H related to the energy? So now, if we want the total magnetostatic energy, this would be big W, we can just integrate, because we have it point by point, we're going to integrate the density. So we're going to integrate the small w over the volume. Mathematically, it's beautiful. It makes lots of sense. And so, we had the energy, how dense it was, right? The energy density, point by point, how dense it was. Now we're just going to integrate point by point over the volume, and then we have the total energy. So this is 1/2 over the volume, B dot H dV, and I can write that as 1/2 mu H squared, again, because they're parallel. And that's it. That's the total energy in a volume, V. I guess I should add the subscript down here, V. Now, the results should not be surprising, because you see we have an energy related to the square of the field. So think about other things that other physical situations that where the energy is related to the square of something. And I'll give you an example that's not electromagnetics. 1/2 kx squared, right, is the potential energy due to a spring. And then if we talk about circuits, the power, which is related to energy in a resistor, is V squared over R, or I squared R. And we had earlier 1/2 Li squared is the energy in an inductor. And so here we see that the energy is related to the square of the magnetic field. So that's a nice result. That's an unsurprising result. It usually happens that it's related to the square of whatever it is, whatever physical quantity we're dealing with. All right, so now we're actually at the point of my favorite topic, my second favorite topic of electromagnetics, and that is magnetic circuits. And that is coming up next, and that is the last topic that we're going to discuss before we get into time-changing magnetic fields. See you then.